So hello everyone. Today's short video is going to focus on Lewis acids and bases. And remember, Lewis acids and bases are electron donors. That's the Lewis base. We also call it a nucleophile. And a Lewis acid is going to be an electron acceptor. We also call that an electrophile. And very often, or at least in some of the simpler cases, things that are Bronsted acids, right, that's the stuff we talked about today in class, are also going to be Lewis acids. And things that are Bronsted bases are also going to be Lewis bases. But there are also a lot of other things that fit into the Lewis category that do not fit into the Bronsted category as well. So it's a little, the Lewis is a little bit more of a broad category. Okay? So if we think about a few of the molecules we looked at today, so things like water, H2O, or hydroxide, right, OH minus, right? So hydroxide we called a strong base in terms of the Bronsted sense. That is, this will readily take an H plus from something. It turns out hydroxide is also a strong Lewis base. Okay, it donates electrons to things. Water. Remember from back in General Chem, water was amphoteric was the word. It could act as a base or an acid. So water is also a Bronsted base, but it's a weak Bronsted base. Water turns out to be a Lewis base. It's also a weak Lewis base. So again, you see the parallel between the two. Once again, the water has lone pairs of electrons. Okay? If we think about things in terms of acids, so if we think about something like HCl, okay? HCl is a strong Bronsted acid. That is, this H readily comes off. It turns out this is also quite a strong Lewis acid. And again, it's this H here, right, that's going to be the acidic part. When we talk about electrons in particular, right, it's because of the polarity, right, of this bond that makes this H the Lewis acid, okay? Whereas up here, it's the simple fact that these things have electrons. And of course, the anion is going to be the stronger, both Lewis base and Bronsted base, than the neutral molecule water. So if we start to look at, right, a few reactions, right, acid-base reactions, and I'm going to take those two that were at the bottom of the worksheet from today's class, right? So we had acetic acid with hydroxide, right? That was one of them. And then we had HCl, hydrochloric acid, with ammonia, NH3. Okay? And you were able to draw the Bronsted acid-base reaction products. This H gets transferred from the acid to the base. So what we end up with for a product, right, is acetate after the H has been removed, and now a neutral water molecule, right? So this was the acid, that's the base. This is the conjugate base of the original acid, and water is the conjugate acid of the original base, OH minus. That's the Bronsted sense. Once again, down here, same sort of a thing. We have Cl minus and NH4 plus as the two products there. So again, the ammonia took the H from the chlorine. So that's, again, this is the acid, that's the base, conjugate acid. Again, that's the Bronsted. Now in the Lewis, these are also both Lewis acid-base reactions. And to think about them in those terms, we need to think about the electrons that are being used. And we're going to use these curved arrows again to show electron movements, sort of like we did when we were moving electrons around drawing resonance structures. So if we think about the electrons here, right, one of these pairs of electrons on this hydroxide, and they're all equivalent, but one of those pairs, we're going to use to form a bond to this hydrogen, which will then make our neutral water, and this OH bond, those electrons get left behind as a lone pair now on the oxygen from the acetic acid. So if I want to use arrows to show that, one of these pairs forms a bond to my hydrogen. So that arrow represents using a pair of electrons to make one of these OH bonds over here. And at the same time, this OH bond, those electrons remain behind as now one of the lone pairs here. So this, thinking about the electron movement, would now be the Lewis way to look at this acid-base reaction. Okay, and drawing arrows like that to show electron movement is something called a mechanism. That is how the reaction is occurring, or where are the bonds being broken and formed. Likewise down here, if we looked at the same thing, we're going to use this pair of electrons from ammonia to form a bond to this hydrogen to make that fourth NH bond. And this bond between H and Cl, those electrons will get left behind as the fourth lone pair now in our Cl minus. So if we wanted to draw this as a mechanism, again, this lone pair is being used to form a bond to H, and this bond is staying behind now as a lone pair on the chlorine. So that would be the Lewis way to look at this reaction, okay? And remember, a Lewis base is typically also the Bronsted base, and we call that a nucleophile. So this OH would be the nucleophile, aka the Lewis base. It's the thing donating the electrons or using its electrons. This hydrogen, so that would be this oxygen here with its lone pairs. This hydrogen here is going to be the electrophile. It's the thing that accepted the electrons from the nucleophile. So again, this H is the electrophile, that oxygen's the nucleophile. Likewise down here, this nitrogen is going to be the nucleophile. That's the thing with the electrons it's going to use to make a bond to donate. And once again, this H is going to be the electrophile. Now, both of these are also Bronsted acid-base reactions. We're transferring H's. But the good part of the Lewis definition is we can completely separate ourselves from talking about H's being transferred and still think of things as nucleophiles and electrophiles, that is Lewis acids and bases. And I have just one or two quick examples of that as well, and then we'll pick this up in class again on Wednesday. Okay? Okay, so let's look at the following. We're going to use OH minus again. You're going to see this is actually a fairly common one with respect to it being a Lewis base or nucleophile as well. But now, instead of something that has an H plus to be used, let's think about something like chloropropane. Okay, and this is one chloropropane. Okay? Now, this clearly is a Bronsted base, but it's also a Lewis base, a nucleophile. Okay, so this is our nucleophile. Okay? Now the question is, where is my electrophile? Where is my Lewis acid? Because this carbon does have some H's on it, as does this carbon and this end carbon. But if we think about the strength of these, the pKa kind of a thing, all of these are CH carbons. So the pKa's of all of those are going to be 40, 45, 50. They're very, 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 very weak. So we are not going to be able to remove any of these H's with that nucleophile. So what are we going to do? Well, this carbon to chlorine bond here is quite polar. Chlorine is much more electronegative. So this chlorine is delta minus, and this carbon is delta plus. So this carbon, by virtue of the fact that chlorine is pulling strongly on the electrons, makes that carbon the electrophile. There's no H on there. These are not acidic. But that carbon itself is the electrophile. Okay, so maybe I'll put this down here. Now in acid-base reaction, the nucleophile forms a bond to the electrophile. So one of these lone pairs we're going to use to form a bond to this carbon. So we're going to make a bond between the oxygen and the carbon That again is our nucleophile and our electrophile. But that would be a fifth bond to carbon. So I cannot do that unless I also break this carbon-chlorine bond and put that pair of electrons on the Cl as a fourth lone pair Cl minus. So what I have as products after this, I still have my original 3 carbons here, but now this carbon on the end that used to have the chlorine is now bonded to this oxygen. And this chlorine has broken the bond to the carbon and taken that fourth lone pair to become Cl minus. And notice that reaction has nothing whatsoever to do with H pluses being transferred. But this is still an acid-base reaction. It is a Lewis base, aka nucleophile, reacting with a Lewis acid, a carbon in this case, that we call an electrophile. And so this is very much the realm that we're going to be in when we talk about organic reactions moving forward. And we'll do some more examples of these sorts of things and talk a little bit in more detail about the Lewis acid and base in class on Wednesday. We'll see you all then.